This video is part of a series on DDD, my DIY Dev Droid. Last time I talked about the throttle control to drive the rotation of the wheels. Now I want to use the sensors on the motors to understand how fast the motor is rotating. This is a step towards speed control automation of the robot. In this video, we're going to use rotary encoders on the motors to sense movement and then calculate the speed of the motors in radians per second. Don't forget to like the video and subscribe, I really appreciate it. Just a quick recap on DDD. DDD is a three-wheeled robot for the purposes of experimentation with robotics and ROS2 using the Raspberry Pi Pico and Raspberry Pi 4. DDD is driven by two 12-volt motors on the front two wheels. These have magnetic rotary encoders on them to sense the speed of the motors. It is these that we'll be integrating in this video. We talked last time about settling the throttle for our robot and then measuring its speed. So if we set its throttle to 50%, then we achieve some speed on the vehicle. And we have to measure that. It isn't, although it's related to the throttle, actually other conditions like going uphill or downhill change what the effect of that throttle is on the actual acceleration and speed of the vehicle. In fact, different motors respond differently, and therefore we may actually see that setting throttles to 50% results in the two motors actually reacting differently on our DDD. We will have to handle that later, but for now, let's just actually measure what the speed is. The motors on DDD both have rotary encoders on board. And I've talked about rotary encoders before on projects. We used one in the video turntable. It was a mechanical rotary encoder, and I used it as a user input device in order to operate the menu. Rotary encoders come in a number of different types. Physical rotary encoders, like I used in that video turntable. Optical ones, like you often see as the center wheel on your mouse. And magnetic ones, which is what's actually on the back of these motors. So you can see just on the back of the spindle there is a magnet that is rotated by the spindle of the motor. There's also then a Hall sensor, in fact there's two Hall sensors there, that detect the pole of the magnet as it goes past, giving us a rotary encoder. So the way that rotary encoders work is two Hall sensors are set at about 90 degrees apart. So as the motor or as the magnet rotates past them, you get two slightly out of phase signals coming from the Hall sensors. So the pink sensor goes high first as it detects the pole approaching it, and then the green sensor goes high, and then the pink sensor drops and the green sensor drops. This is really important because if we go the other way around, obviously the green one will come first and then the pink one second. So it allows us to detect that a rotation is happening and the degree of or the direction of that rotation. The way that we then measure that, or one way of doing that, is to look at measuring each of the four stages as we go through. So I can have the GPIO pins interrupt and tell the Pico that the GPIO pad has gone high or gone low, and we can therefore check to see what the values of the two sensors are. And I can see that it will go through these steps of 1 0, 1 1, both being high, 0 1 and 0 0. It's actually really important because it's got to go through all of those to give me the information that we've managed a complete clockwise rotation, or to go through all of those backwards in order to give me the information that we've gone through a counterclockwise rotation. We class all of those therefore as one tick. The magnet setup on the back of the DDD's motors is quite interesting because actually a complete rotation of the spindle of the motor is actually results in 3 ticks, intriguingly. And then there's a gearbox in there which then drives the wheel. It's in actual fact of terms of those ticks of that complete 4-phase cycle, you actually have 91 of those in an entire rotation of the wheel. And I checked this out and measured this quite carefully because I thought 91 was a really dodgy number when I first sort of worked out that it was approximately that. So I did a whole load of tests, including building a nice cardboard disc to put onto the motor, and then putting an optical sensor on there to actually detect when it's truly actually got to the end of the cycle. So I could run a whole set of calibration tests, and yep, it definitely was 91 ticks. So that's the number I'm working with. So DDD's got those magnetic rotary encoders on board on the back of those motors. The supply for the electronics for those rotary encoder is 5 volts, and it has 5 volt signals levels coming back out of it. That's too much really for the Pico, and so I'm using a logic level converter to go between the 5 volts that the rotary encoder is throwing out and 3.3 volts that is more safe to plug straight into my Pico. If you want to know more about rotary encoders and some more examples, and to go through how they work in a little bit more detail and a little bit slower than I've done in this video, then actually I included them within my Raspberry Pi Pico Micro Projects course. The course looks at them as input devices, but they have all of the same principles that we're looking at today to measure speed on a motor. All the source code I'm going to talk about is in the repo, DDD EXP, DDD Experiment, and it's in Project 2, Speed Meter. The software this time is all very simple, it's just relying on the Pico SDK. We've got the PWM control for throttle that we talked about in the last video, and then I'm doing some interrupt handling to trigger a code to read the rotary encoder, and then some GPIO read code for reading that encoder's coding state. So over in VS Code, I've got our repo, DDD-EXP, loaded up, and we're in the speed meter project. So we've got a couple of additional classes that I'm using for this experiment here, and there's stuff I've used before and wrote some time ago. In order to interface nicely GPIO callbacks and interrupts, I've actually implemented a observer pattern. So we've got a manager class here, which is actually a singleton. You can grab it with the get manager function, and we're going to actually use this to observe the 2 GPIO lines for our rotary encoder. And that's going to use this observer superclass here, and when anything happens, when we get a raising edge or a falling edge on those GPIO pads, we're going to get the handle GPIO function called here. So we can use that with our motor manager. So our motor manager now becomes a GPIO observer, and therefore it's going to implement that handle GPIO function there. And that's what's going to be doing the rotary encoder management and working out, is this a complete rotation and which direction is it going in. Once it knows that, it's actually going to use another function called handle rotate, which is actually going to do the counting of the position as the motor goes round, and therefore the calculations on speed as well. So that's why I'm going to break that up. There's a couple of other definitions that are important to us in here as well. One of which is the number of ticks in the total rotation. That's defined in here, so we've got that. I could have put that as a constant. I've not put that as a constant because when I was using this from calibration point of view, I was actually recalculating that on the fly. It's possible I might want to override it, adjust it in the future, etc. So I've allowed myself to do that. And we've also got encoding values for that rotary encoder. So when we saw those values as the rotary encoder goes through those 4 steps of the first channel going high, then the second channel going high, etc. That is actually encoded here, and I've encoded it for the clockwise direction and for the counterclockwise direction. And the reason I've done that is we're going to use those arrays to step our way through each of the rotations to actually work out when we actually hit a tick and whether that tick is a clockwise tick or a counterclockwise tick. So let's have a look at the C++ code. So let's start by having a look at the constructor. So we saw last time that this is setting up the PWM functions and slicers. It's also adding observers in here on the two channels for our rotary encoder, which I'm calling A and B. So that once we've got those on our input manager observer, we'll get called back on that handle GPIO that an event has happened, either a rising edge or a falling edge. So let's have a look at that handle. This one's there we go. Here's handle GPIO. I've got a bit of code in here still from calibration. Don't worry about that. If it was on the calibration slot and then my slot detector, then I was actually doing some calibration code. Really, this is about every time we get an event and we change from high to low on our A or B channel, we want to actually then do a check to see where are we in that step of that cycle. So where are we in the rising and falling of the that cycle. I'll bung up the graph to just show what's going on as we talk through this. So the first thing I'm going to do is I'm actually going to sample and get the values from both of those channels, and I'm going to then do a little bit of shifting on that to create it into a single value, and that single value I can then compare against the value in the rotary encoder. So the way that this works is I have the value from last time I can actually use to give me the next value from that array. So x last there is the value, the last value I had in from the rotary encoder, and if I use that to look it up into that array, it will tell me what the next value in the array should be. And I can see, okay, so is the next value, is the value I've just read from my rotary encoder what I am expecting to see for the clockwise rotation? Because actually I can get some noise from these, less likely with magnetic rotary encoders than it is with the mechanical ones I've used a lot in previously, but it's still possible to get some noise. So what I want to do is actually say, right, okay, the values I'm getting, are they a valid value, and are they what would be the next value for a clockwise rotation? If they are a clockwise rotation, then we can do some work and say, well, actually we've just done a micro step within that tick and we're going to continue round. So only when that tick actually gets bigger than 3, so we've completed it, do we actually consider that we've actually changed our position and we've gone round one step, in which case I'm going to add 1 to our xpos because we've moved forward. I'm going to do a dual check to make sure we haven't got to the maximum number of ticks. If we have, then we re-zero it. And if we have managed to do a full tick, then we handle a rotation with true, so we're handling a rotation clockwise. And we're going to reset that count number. Then we're going to say that actually our position, our last position, is the current position we've just read from our rotary encoder. And the same thing I do for counterclockwise. So again, check, is the value I've just got and read what I was expecting to see for a counterclockwise rotation? If it is, right, okay, we will decrement the value of x count. When that goes below -3, then we know we are definitely managed a full cycle rotation, and I can subtract from our current position. If our position is going to -1, it's gone negative, then we will actually go to the highest number of -1, so we go back round, and just managing our position within that. And then we're going to handle rotation again, this time counterclockwise, again storing the value of C, so the current rotary encoder value. So that's what we're doing for the management of our rotary encoder, to convert that those signals into a single rotation. So let's have a look at handle rotate. So right, remember this is called every time we have a single tick passed. So I don't need to worry about the number of ticks that have passed. It will always be one, and it will always be one in either direction. Actually, I'm not terribly worried about the direction. I know what direction we're going in. Here I'm really worried about what is the speed. And the speed is really about how long has it been since we last had a sample and last told about a tick. So I calculate the current time now, then calculate how long it has been since we previously had a tick, do a bit of maths to work that out in revolutions per minute, and then that gives us the revolutions per minute number. That looks to me like I actually have an absolute value for the rotations in there that I need to fix. So sorry about that. That's the number of ticks. That should actually be X number of ticks in there. I will fix that, and update the code. Sorry about that. But anyway, this is what this is doing. It's calculating the revolutions per minute. And then it's doing some work to just do a little bit of a moving average calculation on our RPM just to smooth it out a bit. So I'm putting the current value a little bit more strongly than the previous value in order to just hold that in and just give myself a little bit of smoothing. And it's just a bit of weighting in there as well. So we've got these values calculated, so it won't be at all surprising to you that our functions for getting the moving average and getting the RPM are basically just returning this. So there is a little bit of maths in here just to make sure, because I found that I needed a little bit of damping. If I wasn't careful, I didn't actually get stop calculations coming through correctly on the RPM. So there's a little bit of calculations here to say that, well, if I haven't really had a value, then it's actually 0. So I just 0 it here if the number of milliseconds since I last had a value is greater than 250. So if rotation isn't really happening, nothing's happening, I haven't actually been triggered, then it's zeroed. It's really what this bit of logic is doing. It's a little bit of a hack because there is this problem with the way that we are calculating, or I'm calculating speed here, that when the motor stops, we no longer get an interrupt. Therefore, we no longer recalculate speed. So as soon as the motor stops, I don't know, I've got no speed. I'm still reporting the speed as being, 70 revolutions per minute. That isn't right. So we need to say, actually, when you get the RPM, actually, have you had a value recently enough to mean that actually you do have a valid value? If you're not, then the motor's actually stopped. And that's what that bit of logic is doing in there. And then the moving average, which does a little bit check on RPM, because again, if RPM is 0, then the moving average also should be 0. So we just do that calculation and then gives us the moving average. Now, I said we want radians because I'm going to be integrating this lot into the wonderful world of ROS2. And really, in ROS2, the standard definitions of rotation on a motor is in radians per second, not revolutions per minute, which is fine because that is technically the SI units for that, which is what really ROS2 is trying to do. So I'm going to convert this all to radians. So let's have a look at the get average per second radians function here, which is really getting that moving average in RPM, and then it's doing a little bit of maths to convert that into radians per second, and then it's returning that. Pretty simple. I've got quite a lot of maths then going on when I'm calculating the average radians per second. Is that a problem for us? I don't think so. it is possible I might have to come back and refactor some of this work at a later date and switch it to be natively radians per second calculations. I don't know. We will find out as I go. But that's the calculations I'm doing. That's how it works. In tests so far, everything looks good and correct. So let's have a look at main and what I'm doing in main to test this stuff out this time. Well, main's really very simple. Just like last time, I'm setting up two motors, left and right, and then I'm going to throttle them up through a set of throttle steps from 0.3 to just under 1, well actually 0.9, in 0.1 revolution cycles. And those numbers are in throttle, so they're percentage of throttle. So 1.0 is 100% throttle, 0.3 is about 30% of the throttle. We're going to throttle the two motors. We're going to throttle them in different directions so that they appear on my video to turn the same way on the robot, because obviously one is rotated 180 degrees to face the other way on the back of the robot or front of the robot. That's how the wheels look. And I'm then going to run a little loop here at half-second intervals, and I'm going to print out the average radians per second of both the motors as I keep reading them. So we should see what the effect of the throttle is over about 20 sampled values through that loop. And that's what I'm interested in seeing, and seeing how accurate those two motors are. So let's have a look at a demo now. So here we have DDD motors running, and we're going through and setting the throttles and then measuring the speed between the left and the right motors. And you can see that actually the speed being measured is pretty close across the two motors, but although they're being set to the same throttle, and over time I'm printing that speed out every half a second, these speeds are actually just slightly different between the two. And that's something that we need to come back to and look at in the next video. So we can now control the throttle and see its effects in terms of rotational speed achieved. We've seen that the motors don't turn at exactly the same speed for the same throttle. Local friction, like hills, will make this worse. So for a useful robot, we'll need to have control logic to manage the actual speed of the motors. That will be a future video. Thank you very much for watching. Please like the video as it helps others find it. Please subscribe and hit the notification button so you don't miss that next video. Goodbye for now.